Hey everyone, and welcome to this explainer brought to you by Forge College. I am super excited to be your guide today. So, in our previous lesson, defining and initializing structs, we learned all about building individual, custom machined gears for our engineering toolkit. And, structs are absolutely fantastic on their own, but a single gear doesn't really make an engine, right? Today, we're building the whole gearbox. We're going to take those individual gears and figure out how to align them, organize them, and run them efficiently on the blockchain. This is arrays and access patterns.
All right, let's jump right in. Here's our engineering blueprint for today. First, the array assembly line. Second, storage versus memory. Third, push, pop, and remove operations. Fourth, gas-safe iteration. And finally, we'll wrap up with AI workflows. Okay, section 1, the array assembly line. How we actually go about organizing hundreds of structs. So right out of the gate, here is the big question we absolutely have to answer. How do we store many structs without just completely breaking the blockchain? I mean, in traditional programming, you'd probably just throw a million items into an array and let your server's RAM sort it out. Easy, right? But in Web3 engineering, we're up against the ultimate villain, the gas spill. Every single time we store, move, or even just read a piece of data on-chain, we are paying for it. If our mechanical design isn't incredibly precise, our smart contract is going to quite literally run out of fuel. To solve this, we rely heavily on something called the dynamic array. Basically, a dynamic array is a collection of elements, like our custom structs, that can grow or shrink in size while they're on the blockchain. Unlike static arrays, which are kind of locked into this rigid, fixed size from the very beginning, dynamic arrays give us the flexibility to append new data on the fly as our contract operates. They're your primary go-to mechanism for holding collections in your contract state. Moving on to section 2. Storage versus memory rules. Basically, the underlying physics of our blueprint. Let's think back to that golden rule from our previous lesson. The crucial point here, the thing you really need to internalize, is the difference between storage and memory. This is literally the one rule that predicts almost every weird surprise you'll ever encounter with arrays. If you access an array element directly in storage, you're creating a persistent reference, meaning any tweaks you make permanently alter the blockchain state. But if you pull that element into memory, you're only working with a transient copy. You can mutate that memory copy all day long, and the original array back in storage doesn't change one bit. It's kind of like the difference between permanently welding a piece of metal on the assembly line versus taking a Polaroid picture of it and just drawing on the photo. Section 3. Push, pop, and remove. Getting our hands dirty with the mechanical operations. For dynamic arrays, our two most fundamental operations are push and pop. Think of these like machines that only do their job at the very end of a long conveyor belt. Push lets us cheaply slap a new element, like a brand new struct, onto the end of the array. And pop lets us cheaply snatch the last element right off. Because both of these operations only ever touch the absolute end of the line, they're incredibly gas efficient. They don't mess with any of the other elements sitting on the belt.
Now here's where it gets really interesting. Take a look at these two different mechanisms for removing an item from the middle of an array. The first one is an ordered remove. This is your classic conveyor belt. If you yank an item out of the middle, every single item behind it has to shift forward one space to fill the gap. Sure, it preserves your pristine order, but it is a total gas nightmare for large arrays, because you're paying to move every single shifted item. The second approach? The swap and pop. This is essentially a trapdoor. You grab the very last item in the array, swap it into the empty space you just made in the middle, and then you just pop the end of the array. It's totally chaotic, it completely ruins your original order, but man, is it gas efficient, because you're only moving one single item. As an engineer, you've got to choose the pattern that fits what you're actually building.
Section 4. Gas-safe array iteration. How to survive the stress test. Let me give you a very serious, though kind of funny warning here. Returning massive arrays will literally bankrupt your gas budget. If you try to write a public function that loops through a huge array and returns every single heavy struct inside it, your gas costs are going to multiply insanely fast. Eventually, you'll slam right into the block gas limit, and your transaction is just going to catastrophically fail. The machine completely breaks.
So how do we prevent this? We use gas-safe iteration techniques. Instead of trying to return these massive bulky arrays, we calculate and return aggregated values instead, like, say, just a simple sum of the IDs. Or if a user interface absolutely needs the data, we implement pagination, so we're only handing over a small, manageable slice of the array at any given time. Another trick is to just return a list of lightweight identifiers instead of the full, heavy structs. These are the real-world engineering habits that keep your smart contracts actually usable. Section 5. AI-assisted coding workflows. Basically, your personal robot QA assistant. Because let's be real, array manipulations, especially stuff like shifting and swapping, can be incredibly tricky to write from scratch. But we can use AI to massively speed up our builds as long as we stick to a strict, disciplined cycle. You don't just ask the AI to write the whole contract and blindly deploy it. No way. You work in cycles. Step 1. Generate a candidate snippet. Step 2. Compile it locally. Step 3. Run a unit test against it to catch nasty stuff like out-of-bounds errors. And Step 4. Refine the code by feeding any of those failing tests straight back to the AI. Generate, compile, test, refine. To actually get good results, you've got to be a bit bossy with your prompts to force the AI to give you highly testable, deterministic code. Always enforce the Solidity 0.8x version. Tell it exactly what function names you want. Explicitly ask for bounds checks using require statements. And absolutely most importantly, always request a unit test scaffold, like a hard hat test, so you can instantly verify that your swap and pop logic is actually safe. Finally, let's recap and sign off on today's blueprint. We covered a ton of ground today. We saw that accessing an array element in storage permanently mutates your state, while pulling it into memory just gives you a safe copy. We looked at the incredibly expensive order-preserving removal and contrasted it with our new best friend, the chaotic but cheap swap and pop technique. And we established that gas constraints totally dictate how we loop through data, meaning we have to rely on aggregates and pagination. Which leaves us with one last, slightly terrifying question. What actually happens when an array gets so pathologically huge that it breaks the machine entirely? Like, how do we even design for upgradability when that disaster strikes? Well, that is exactly what we're going to dive into in our next explainer on edge cases. Until then, go test out these mechanical principles, and be sure to check out forge.college to level up on even more Web3 engineering topics. Thanks so much for hanging out with me on this explainer by Forge College. Catch you next time.